linear functions. So hidden in the word linear is line, and so this means that you're going to have like a constant relationship that can be represented by a straight line. I'll just take advantage of the fact that there's a graph here. Like if you put more time in, your pay really stays pretty constant for a while, so your pay is going to just increase at a steady rate. And when I say your pay, I really mean the amount of money that you have in your pocket, not like your salary. Similarly, if you have a certain amount of money, and you just pay it towards a cell phone bill month to month to month to month, you're going to eventually run out of money at a constant rate. So having discussed the triangles, toothpicks problem at length, let's check out what that means for these big ideas of being able to identify linear equations, the intercepts, and the zeros of something. So with the linear equations, let's look at the ordered pairs. Well, when we built one triangle, we used 3 toothpicks. 2, well, we needed 2 more to keep it the pattern we had. 3 was made with 7 toothpicks, and then 4 triangles was made with 9. And so I went through that quickly because this is an activity that we've done in the past. Now we can represent this as a table. 1, 3, 2, 5, 3, 7, 4, 9. On the graph, because of the space I have, we'll just treat this as 1, 2, 3, 4. So I'm over 1, up 3, over 2, up 5. And even though these would be discrete events, you'd have to have that very first toothpick to begin from. And we'll draw it like this. Even though for our toothpicks problem, we're not really dealing with negative toothpicks or negative triangles. And then for the mapping, as we continue the previous section's idea, 1 gave us 3, 2 gave us 5, 3, 7, and then 4, 9. And as we look at this, you would also know that it is a function, and all of these would be functions because it's the same problem, and all linear equations are linear functions as well. I'm going to use a different color just to show that we rise 2 for every 1 that gets added, 2 for every 1 that gets added, and then in the graph we go up 2 for every 1 that was added, 2, 1, and then you can kind of look at the mapping and see that as well. But I can really truly believe that this is a straight line and we are dealing with something called a linear equation. Now if I look at the intercepts, here's the nicer view. This is the x-axis, this is the y-axis, and the intercepts are where your x and y axes get intercepted or run into. So if I look at this first, more clear one for me, where I see a value of here, that would be not the x-intercept but the y-intercept, because it's where the line runs into the y-axis. So the y-intercept there would be when x is 2. I'm sorry. The y-intercept would be y equals 1. And I won't talk too much about the zeros right now because it's going to come up later, but this would be like a fraction setup here. So when y would actually be 0, what's the x value there? And we'll leave it at that for now. Now the standard form of a linear equation. If you want something to be a linear equation, then it has to be able to be written as some number a times x plus another number times y equals 0. Now that doesn't mean that I can't have, my x's and stuff over on the other side. You totally can, but it has to be able to be written this way. And now there are constraints that go with this. When you create a equation in standard form, the rule that people just agreed to is that this has to be this a has to be a number that is positive. So a has to be positive. So if you ever wrote an equation where you had like a negative out in front, you would just, flip the signs on everything and fix that problem really easily. So when you conclude and you have standard form, the deal that is that has to be positive. And so when I say it has to be positive, here it is, greater than or equal to 0. It can be 0, that's totally okay. That just means this would drop out. And you'd only have y in the equation and other numbers. And the deal is, both of these can't both be 0. If they both were 0, that would mean that you'd have no x showing up, because anything times 0 is just 0. You'd have no y showing up, so it really wouldn't be like a graph at all. And then the other deal is that a, b, and c have to all be integers, meaning you would not have 5 halves x minus 3 halves y equals 1. That's no good. And not only that, their greatest common factor has to be 1. So that means if I have like 4x plus 2y equals 4, well, this could be simplified where they all would get divided by 2. So it just really means that last thing, you have to have it simplified. And trust me, once we get into the problems, this will be way, way, way more clear. Okay, so determine whether it's a linear equation. If so, write the equation in standard form. So for this very first one, I'm going to kind of pan in just so I have more space to write in. So I'm rewriting number 1, y equals 5 minus 2x. And as I look at this, I don't see any exponents. I don't see anything going on where I'm actually like dividing by a variable. I also don't see anything strange where x is being multiplied by y. They're all separated by these minus signs, or maybe they're on the other side of an equation altogether. So to me, this looks like we could turn it into ax plus by equals c. And as we look at this, first of all, what's different from ax plus by equals c is that now the x and the y are both on one side of the equation. So that means that we need to get ax plus by. We need to get the x's and y's over to one side. Now, you can always try to avoid negatives. And since I do want to avoid a negative in front of my x value, because that's the rule, I'm going to add 2x to both sides. Now, if that ends up resulting in more work than you want to be doing, then you don't have to do it that way. You could, deal with y first. Doesn't matter. So then I rewrite 2x in the front plus y equals 5. Now, you have to say to yourself, well, we did start to change this, and the reason we started to change it is because the original problem instruction said, determine whether it's a linear equation. So I felt like, yes, it is. So if so, write it in standard form. So now that we're heading towards standard form, 2x plus y equals 5, let's look at our rules. Does it look like this? Absolutely. We have something times x plus something times y. It would be 1. We don't need to use that. Is equal to something on the right side. Well, the first requirement is that a has to be positive. A is positive. They both can't be 0. Well, neither 2 or 1 are 0, so we're good there. And then the other thing, too, is they all have to be having a greatest common factor in integers of 1. And when I look at this, it's like, well, I could divide by 2, but then I'd have a fraction, and I'd be dealing with things that were no longer integers. So this is the final result. This is the equation rewritten in standard form. And yes, it is a linear function. Yeah. Let's look at 2. So you should always rewrite every problem. So here's 2xy minus 5y equals 6. Well, I scanned through it. I don't see any exponents. But I do see x getting multiplied by y. And, no matter how I try to change this or whatever, it's not going to end up working out. So this is not a linear equation. So we would just say not linear. Looking at 3. Well, here we have 1/3 y is equal to negative 1. And as I look at this, well, there's no x, and that's a little bit peculiar. But a actually could be 0, so it's okay for x to go away in this. So even though I don't see an x, this is going to work out just fine. But the issue is you can't have fractions. So we're going to multiply everything by 3, which cancels this out, and I'll have y equals negative 3. And I'll show this in red because I don't want you to write this. But if I had 0x plus 1y equals negative 3, it's a little bit more clear to me that it does actually match the form. But no, I don't want you to do this. Yes, this is linear, and once you would get to this point, you could box it and be done. Make use of the space however you need to. You might need extra paper, I'm not sure. If I look at this, I scan through, and I see an exponent. And if I wanted to pull up Wolfram Alpha or something and graph this, I'd see it's actually parabolic. It's not linear at all. And because of that, we're going to write not linear. And if you don't rewrite the problem, you're kind of like shooting yourself in the foot, because later when you study from this, it'll be nice to glance at your notes and know actually why you wrote that. So we just took care of these 4 problems where this problem 1 and 3 were linear, but 2 and 4 were not. A little explanation on standard form, and also referencing the toothpicks problem.